the layout of a quick return mechanism of the oscillating link type for a special purpose machine. The driving crank BC is 30 mm long and time ratio of the working stroke to the return stroke is to be 1.7. Determine the dimensions of AC. So here is the given mechanism ABC, where BC is the crank. Let us say alpha is the angle made by the crank with the axis A. Let us say this is alpha and this is the point C and A, B. So here we will have to find out the dimension of AC, and but we know that here the driving crank BC is 30 mm long. So here BC is equal to 30 mm, and another given data is the time ratio of the working stroke to the return stroke is to be 1.7. Actually here the time ratio of working stroke to return stroke is equal to 360 minus alpha by alpha and is given by 1.7. Sorry, it is generally indicated by alpha by 2. So here it is alpha by 2, and here the time ratio of working stroke to the return stroke is equal to 360 minus alpha by alpha is equal to 1.7. So which gives a value of alpha is equal to 133.3 degrees, and here alpha by 2 is given by 66.65 degrees. Now let us say ABC is right angle triangle at some position. So at that position the angle made by AB is equal to 90 minus alpha by 2. So which gives a value of sin 90 minus alpha by 2 can be taken as opposite side by inside side, that is opposite side by hypotenuse. So which is equal to BC by AC. So and we know that BC, that is 30. Now from this equation AC is equal 30 by sin 90 minus alpha by 2, that is sin 90 minus 66.65, which gives a value of 75.7 mm. So this is the dimension of AC, and in the option the right option is D. D is the right answer. A steel plate of thermal conductivity 35 watt per meter Kelvin having dimensions 1 meter into 0.5 meter into 0.05 meter is maintained at 400 degrees centigrade at its top surface. If the surrounding air is at 25 degrees centigrade and having convective heat transfer coefficient of 20 watt per meter square Kelvin, calculate the temperature at the bottom of the plate. Assume heat loss by radiation from the surface is 500 watts. Here we will have to find out the temperature at bottom of the plate. So that is nothing but first we will have to find out, for that purpose first we will have to find out the conductive heat transfer through the plate. So the conductive heat transfer through the plate is given by K delta T by del X, where del X is the thickness of the plate and delta T is the temperature between inside and outside, top surface and bottom surface of the plate, and K is the thermal conductivity and A is the surface area of the plate. So this conductive heat transfer is equal to the sum of the radiative heat transfer and conductive heat transfer of the one side of the plate. So that is equal to, here Q conductivity can be written as Q radiation plus Q convection. So here the radiative heat transfer is directly given as 500 watts, and we will have to find out the convective heat transfer. So that is equal to HA delta T, where H is the heat transfer coefficient and A is the surface area of the plate, and delta T is the temperature between the temperature difference between the plate and surroundings. So here it is equal to 20 into the area of the plate is 1.1 into 0.5, and the temperature difference between the plate and surroundings is 400 minus 25, which gives a value of 3750 watts. Now the total conductive heat transfer is equal to 3750 plus 500 watt radiation, so which is equal to 4250 watts. So now substitute all the values in the conductive heat transfer formula. We can get here 4250 is equal to, here thermal conductivity of the material is 35 and surface is 1 into 0.5, and here the temperature difference is inside temperature minus 400 by heat is the thickness of the plate, that is 0.05 meters, which gives a value of inside temperature or bottom surface degrees centigrade in the option. The correct option is A. A is the right answer. Turbine plant operates between 5 degrees centigrade and 835 degrees centigrade. What is the pressure ratio at which the cycle efficiency will be equal to Carnot cycle efficiency? Here the options are 136.4, 116.4 and 126.4 and 146.4. So here we will have to find out the pressure ratio of the gas turbine cycle at which the cycle efficiency will be equal to the Carnot cycle efficiency. Here we know that the Carnot cycle efficiency is given by 1 minus T2 by T1. And generally the gas turbine cycle efficiency is given by 1 minus 1 by Rp power of gamma minus 1 by gamma, where Rp is the pressure ratio. So we will have to find out this pressure ratio, yet the cycle efficiency will be equal to the Carnot cycle efficiency. Here just equate these two efficiencies. So here we get T2 by T1 is equal to 1 by Rp power of gamma minus 1 by gamma. And here we know that the gas turbine plant operates between 5 degrees centigrade and 835 degrees centigrade. So here 5 degrees centigrade is the minimum temperature, that is T1 is equal to 5 degrees centigrade and T2 is equal 835 degrees centigrade, where T1 is equal to 278 Kelvin and T2 is equal to 1108 Kelvin. Now substitute these values in the given equation and take gamma is equal to 1.4 for the ideal cycle, so that it gives a value of Rp that is equal to 126.4. So in the option the correct option is C. C is the right answer for the